What actually is a buck converter? Well, let's take a look at the components making up this single buck converter. Now first off, we have these two tall brown cylinders. They are electrolytic capacitors, used to store energy and smooth out voltage ripple. Next we have this green toroid with enamelled copper wire wrapped around it. This is our inductor, which again stores energy, though this time for smoothing current ripple. And then finally we have these two black devices, which are the most important. They are our transistors, or more specifically MOSFETs. These are the electronically controlled switches that we can use to change how the circuit is connected. One of the MOSFETs is connected to the positive supply, so in this case 12 volts, and it's that one. And the other MOSFET, this lower one, connects to the negative supply, so in this case 0 volts. And the other terminals of both of these MOSFETs are joined together to form a very common configuration known as a half bridge, which allows us to easily switch between two voltages, positive and negative, by turning on the high or low side MOSFET respectively. To try and illustrate this concept a bit more clearly, I've created this, a manual half bridge. You can see, just like the buck converter, we have a positive and negative supply, the red and the black, and the blue is our output. Flicking the switch will change which of these two wires the blue wire is connected to. As you can see, because when I flick the switch, the multimeter reading goes from 0 volts up to 12 volts, and then when I flick it again, back to 0 volts. But how does this give the 1 volt we need to supply a CPU? It's either on or off. 12 volts is going to fry your CPU instantly, and nothing's going to happen at 0 volts. Well, all we need to do is flick our switch very quickly, and then control the amount of time it's on and off. And the ratio between the amount of time it spends on to a total period is the same as the output voltage to the input voltage. For example, if I spend half my time with the switch on and half my time with the switch off, the average is going to be half of the input voltage, so 6 volts. Or if I want my 1 volt for a CPU, then I put it on about 8% of the time, and the rest of the time I'm connected to the negative supply, or 0 volts. As the concept of having the switch on or off is fundamentally digital, I've temporarily replaced our multimeter with an LED, so that turns on when I flick the switch and back off. And hopefully with this LED I can illustrate the difference between a half bridge and a buck converter. Right now this circuit represents just a half bridge connected to some kind of load. As mentioned before, I can turn it on and off very quickly, but the load still sees the voltage turning on and off. So for a CPU, you're still going to turn it on, 12 volts, bang. What a buck converter does is it adds an output filter to this half bridge to smooth out that on and off into more of an up and down. So let's add an output filter and see what happens. And would you look at that? This is starting to look a bit like a buck converter with a cylindrical electrolytic capacitor here to smooth out our output voltage from the half bridge. And you can see how the LED now slowly turns on and slowly turns off. So you can probably imagine if I flick this quickly, the LED is not going to go off, it's just going to sort of ripple. There we go. Now let's see if we can measure that voltage with the multimeter. Can you see? It's about 3 volts, 4 volts. It's a little bit tricky for me to modulate the on to off ratio, but let's give it a go. So that's now off more. You can see it's more like 2.5 volts. And if I go on more, 6 volts. Amazing. And this whole process is known as pulse width modulation and is one of the absolute fundamentals of power electronics.